The title of this lesson is Moments. So we're going to be looking again at moments about a pivot. Now firstly, we need to look at the key terms. We have balanced, equilibrium, moment, center of mass, and uniform. Before we start, I'd like you to write down the equation for a moment and state what is meant by balanced. And then consider, how do you find somebody's weight using an old medical balance? Notice there is no digital scale there, but there are several weights that are being used. So we have a glossary of terms here. Balanced is when two quantities are equal in magnitude but opposite in direction. Equilibrium is when an object is either stationary or moving at constant velocity. This is because there is zero resultant force and there is no overall moment. So it's neither being accelerated nor is it being caused to turn. A moment is the turning effect of a force. The center of mass is the average location of the mass in an object, or it can also be thought of as the point in an object that weight appears to act from. And finally, we have uniform. Uniform is a word we use to describe anything that is a constant density throughout its structure. So generally, when we have a uniform object, we can assume that the center of mass is in the center of the object, because the density is constant throughout. It's a consistent material. So on screen we have a uniform rod. This could be a meter rule, for instance. So its center of mass we can assume to be right at the center at the 50 centimeter mark. That means that its weight seems to act from that central point. So notice this is both the average location for all the mass, and it's also the point about which the weight appears to act. So let's look at our first pivot situation. When the pivot is directly below the center of mass, what we find is there is a support force which is equal in magnitude and opposite in direction acting from the pivot upwards. So these forces are equal and opposite, so they are balanced. Now the question becomes, what happens if the pivot is not directly below the center of mass? So in this situation, we have the center of mass still in the same location, pulling it down with a force F1, I've decided to call it. And we also have a support force S. Now in this particular instance, the ruler will begin to fall and it will begin to turn. So what happens if we add in F2? If we add in a weight that is far to the left of the pivot that can balance F1 so that we can have a situation of equilibrium. Well, the first thing we need to recognize is that we have these two distances now. The distance between F2 and the pivot is known as D2, and the distance between F1 and the pivot is known as D1. We also have a support force which acts upwards at the pivot. This is because if we only had F1 and F2 acting on it, then there would be a downward resultant force, and so the rod would accelerate. However, because we don't have that, we are in equilibrium. So we notice now that if we're in equilibrium, the total force up must be the same as the total force down. Now similarly, if this is balanced, and again in equilibrium with regards to moments this time, we can say that the anti-clockwise and clockwise moments must be the same. Now the key here is to recognize that we can now represent this mathematically. For equilibrium, the total force up and down is the same, and so therefore F1 plus F2 is equal to S, the support force. For equilibrium, the total clockwise and anti-clockwise moments must also be the same, and so we have F1 times D1 must be equal to F2 times D2. Now it's important to notice and recognize how we can make these two equations from the situation we have, thanks to that word equilibrium. That allows us to put an equal sign in there. So let's take a look at this scenario. We want to find the weight of the meter rule, but we don't have a normal balance, we don't have a scale. So what we can do is we can use a known weight that we already have. So I've chosen to use a 1.2 Newton weight. We can then attach that weight at a known distance from the pivot, and since it's a uniform rod, we also know where the center of mass is, so we know at least where the weight is acting from, and we can use moments and the idea of equilibrium to calculate the weight of that ruler using a known weight set at a known distance from the pivot. So the first thing we do is we notice that the clockwise moments, F1 times D1, is equal to the anti-clockwise moment, F2 times D2. We can substitute in our numbers, so instead of D1 I'm putting 0.15. That's because 0.15 is the meters and 15 centimeters is 0.15 meters. We also have 0.3 times 1.2. We can then rearrange that and work out that F1 is 2.4 newtons. Next, let's imagine that we have more than one weight. In this particular case, we have several distances. Now, the trick here, the thing that usually catches people out, is to work out which distance is which. So we have our pivot there. So we know our anti-clockwise, that will be anything moving against the clock, so that is F3. We know that the moment is F3 D3. Where F3 we don't know is what we're looking for here, and D3 is 30 centimeters, so 0.3 meters. Meanwhile, we also know what the clockwise moments can be written as. In this case, F1 D1 plus F2 D2. We have two objects causing a clockwise moment. First of all, we have the center of mass of the ruler causing a clockwise moment, and we also have the weight that we've added causing a clockwise moment. So we can rewrite that as m equals 2.4 times 0.15, so that's F1 is 2.4, D1 is 0.15 meters, and we can then add in 3 newtons times 0.55. And here's the thing to notice. 0.55 is the distance from that weight to the pivot. So that's 40 centimeters plus 15 centimeters. Once we have both of those, if we know this is in equilibrium, we can simply say that the anti-clockwise moments equal the clockwise moments. And so here we now have a full equation. We can collect the terms together and make F3 the subject of the formula, and that gives us 6.7 newtons. So the weight of F3 must be 6.7 newtons. The next scenario is a little more complicated. What happens if we have a rod with two supports or two pivots? Now in this case, we can recognize again that the total force upwards must be equal to the total force downwards for this object to be in equilibrium. We can also say that clockwise moments and anti-clockwise moments must be the same. However, there is going to be a slight difference here. So firstly, for our up force and our down force, we can simply say that F is equal to S1 plus S2. However, for the moments, you must choose where the location of the pivot is. Now we have three locations where we can choose the pivot: location A, location B, and location C. Now, technically speaking, we have even more locations. We could choose the pivot to be at the far left end or the far right end, or in fact anywhere. But for simplicity's sake, we will choose A, B, or C. So for A, we say that the clockwise moment equals the anti-clockwise moment. So we have F times D1. So if your pivot is at point A, you have F times D1 is your clockwise moment, and you have S2 times by the total distance D1 plus D2, and that would be your anti-clockwise moment. Now you'll notice S1 does not appear. That is because S1 is at a distance of 0 from the pivot, and so we can ignore it. It also, given that it's at the pivot, doesn't have any clockwise direction or anti-clockwise direction. The second choice for the pivot B, we have S1 times D1 is the clockwise moment, whilst S2 times D2 is the anti-clockwise moment. Now this does appear to be the easier one to do at the moment, but you'll soon see it's actually the more difficult one to use to solve to find S1 and S2. And then we have C. If we choose C as the pivot, we find that the clockwise moment S1 multiplied by D1 plus D2, whilst the anti-clockwise moment is F times by D2. And finally, we must also remind ourselves the very important rule that the total force up and the total force down is equal. So F is equal to S1 plus S2. So we're now going to look at some calculations on how we would find S1 and S2 if we know F, and we also know D1 and D2. So let's choose our pivot to be A for this first example. So we have our equation that F times D1 is going to be equal to S2 times D1 plus D2. So that's simply our moments being equal to one another. And we also have that F equals S1 plus S2. So we'll start by substituting in some numbers. So instead of F, we're going to write the 20 newtons that we've been given. Instead of D1, we're going to write 0.3. Now S2, we don't know, and is what we're going to look for. Meanwhile, the total distance from S2 to the pivot A is 0.4 meters. Once we've done that, it's simply a matter of making S2 the subject of the formula and finding our answer for the support force 2 is 15 newtons. So the force acting upwards at S2 is 15 newtons. Now this is very important in engineering because this tells you how strong that pivot needs to be. Finally, if we want to find S1, we can simply put that into our equation for the upward and downward forces. So we have 20 equals S1 plus 15. That's pretty obvious. S1 must therefore be 5 newtons. Let's do a similar scenario, but now this time using B as the pivot. So firstly, we have clockwise is S1 times D1, and anti-clockwise is S2 times D2, so we can say that they are equal to one another. Next, we also have that F equals S1 plus S2. Now we have a problem here because B does not include the force F. So what we can do in this scenario is we can rearrange our upwards and downwards forces to show that S1 is equal to F minus S2. And we can take that and substitute it in to the equation for the pivot B. So instead of S1, I'm now writing F minus S2. We multiply that by D1 and then equals S2 times D2. So F was 30, so instead of F we write 30, Then we've got 25 centimeters, that's 0.25. Then we have S2 and multiplied by 0.12. Now here we have to open those brackets up, so we have 7.5 minus 0.25 S2 equals 0.12 S2. Collect the S terms together, and we end up with 0.37 S2 equals 7.5, and therefore S2 is 20.3 newtons. We can then simply return to our upwards and downwards forces, and we want to find S1, so we simply say S1 equals 30 minus 20.3, and that gives us an answer of 9.7 newtons. So here we have C as the pivot, and you'll notice this will be very similar to A as the pivot. So if C is the pivot, we could ignore the force at C. We could ignore S2. So we have S1 is multiplied by D1 plus D2. That's our clockwise moment. And we have F times D2 as our anti-clockwise moment. And these must be equal to one another for this system to be in equilibrium. And again, the force up and the force down must be equal again for it to be in equilibrium. So we can substitute in our numbers, and we find that S1 brackets 0.35 plus 0.14 is equal to 15 times 0.14. Collect those terms together inside the brackets because they aren't multiplied by anything. And we have 0.49 S1 equals 15 times 0.14. Let's make S1 the subject of the formula, and that gives us 4.3 newtons. And then finally, if we want to find S2, we can substitute in the numbers where we find 15 equals 4.3 plus S2, so therefore S2 is 10.7 newtons.